Here we go. Ionization energy. 30 seconds. Tell your partner everything you remember about ionization energy. What do you think? Down to 10 seconds. 10 seconds. Okay. So here's another question. If you were absolutely forced and someone said, hey, I'm gonna steal your lunch unless you give me an example of an element that has a low ionization energy and a high ionization energy. Tell your partner, just, it doesn't have to be the specific one, but tell them one that has a lower ionization energy and has a higher energy, whatever. Okay. Oh no. No, I don't need copies. I don't need copies. I need a ream of white paper. Yeah, just like blank paper to print. It's okay. Okay, here we go. So if you were forced, where would your eyes look for a low ionization energy atom? On the left side of the periodic table. And then you would think, well, if that's the low, then where's the high? Over there, right? No, the middle. You on drugs? Don't answer that. It is not the ionization energy, but are they related? 100% related. The less attractive the electron is to the nucleus, the less ionization energy. So over where fluorine, it has high Zeph, high attraction to the electron. It's going to be way hard to remove that. So we don't. Fluorine doesn't lose electrons in a bond. What does it do? It gains them. All right. So here we go. I feel like we're okay, sort of, with ionization energy. The trends, the bell rang right at this moment. So you'll notice an extremely high ionization energy for helium. So is it involved in chemical bonds? Nope. Like we could force it to, I guess. Like if we put a tremendous amount of energy in to remove an electron, like we could get it to bond with something, but it's just not going to happen. Okay. All these noble gases are really high, correct? And that's why they're noble gases. Now down here, they get low enough that they're kind of close to other things. So xenon and radon do form bonds. They're really weird ones, and we'll talk about them later in the year. But generally, noble gas is nothing. All right. The non-metals, pretty high first ionization energies. So they don't, like, they never lose electrons. All right. Over here, pretty low. Hydrogen high, but still way lower than helium, right? So Davis, your two that you said would work fine. But just know that we have high and we have low. All right. We also know we have big and we have small. So do you think that the size matters? Yeah, the smaller it is, the higher the Zeph, the higher the Zeph, the higher the ionization energy. Pretty easy. Okay, so on the test, you're going to be asked ionization energy trend, and you just need, like, it's up to you how you label. Well, no, I guess the test tells you how to label it. And you should know that it increases as you go up and it increases as you go to the right. Easy enough? That's what I need. Thank you. Yep. So here's your explanation. As one goes down a column, less energy is required to remove the first electron. No, that doesn't say why. but whatever. For atoms in the same group, Zeph is essentially the same, but the valence electrons are farther from the nucleus. Okay, so the first one is just stating the fact. This one's telling you why. So if you're all in family 1, Zeph is still 1, right? But the electrons are farther away because we added what S word? Shells, the shell model. Thumbs up. Okay, side to side. Generally, as one goes across a row, it gets harder to remove an electron. Or this could be rewritten. Generally, as we move from left to right, the ionization energy increases. All right, and that is because as you go from left to right, Zeph increases. Now, look at these trends. They are general, but they're definitely not perfect, right? Nothing in chemistry is perfect. Yes, Corbin. Why do they go down a little sometimes? Well, why don't we talk about our discontinuities? Never mind. That was like the story of my life in high school. Like I have it all set up, and then I'm like, oh, you're a failure. You forgot for a second, didn't you? All right. You do not have to explain this anymore. They've really made chemistry soft. If you'll notice here, it has 1, 2, and then a drop. 1, 2, and then a drop. All right, this one's a little bit weird because we get into the D's. But let me just explain it with the first two because it makes sense, hopefully. Yep, you have one S2 or whatever, you have your 2 and your S's, and then you have your P. What it's saying, just quickly, is it's a little bit harder to remove one of these that's paired than that loner right there. But it's not a lot harder. Like it's a bigger deal already as you go lower, but it's easier to remove a single P than to break a full S is the answer. And then the next dip, it's the same idea. It's right here. It's easier to remove that one than it is to remove that from when it's paired. And you don't have to explain the discontinuities anymore. But it's all about when a shell or a box or a cloud gets full and it switches. Okay, but that's where the dips come from. But generally speaking, it increases as we go from left to right. But it gets really weird when you get to the D's. Boom. And there's a million exceptions. But in general, that's what we're going to worry about. Okay with that? What's that? Yeah, there's exceptions to almost every single thing I teach. And it sucks. Can't think of one. All right, so summary so far, all this was already on the previous summary. That's why it's white. So we're just adding this. Metals have low ionization energies because they have low Zeph. Okay with that? Non-metals have high because they have high Zeph. And remember, all this crap is ultimately related to Coulomb's law, right? It all goes back to Coulomb's law. All right. Ionization energy increases as you take off more and more electrons because you are removing an electron from an increasingly positive atom. So ionization energy 1 is usually less than ionization energy 2. Thumbs up. Okay. Ionization energy takes a large leap when you try to remove a core electron because you are breaking a completed shell. Okay, we talked about that, but let me just draw it out super quick. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I'm not talking about neon. I'm just talking about something that has 2 in whatever this S is. You with me? We don't care what it is. But to remove the first one, ionization energy 1, let's just say it's 500. To remove the second one, let's say it's around 1,000. But to remove a third one, that's what I meant. We'll say it's like 10,000.
When all electrons become valence electrons,
then yeah, you'd have 7 valence electrons now, and it'd be PO'd. I edited that. So that's my conscience. Abby is not.
You haven't even read the board today.
Oh, I have not. Maybe I should. Okay. There's a question on the test. Now, it's a take home, so it's not going to be hard. Not this board, Miller's board. Or is it my board? Yeah, Miller's board. She's that passive aggressive. There's a question on the test that will say an atom has the following 3 ionization energies. So 1, 2, 3. And it's like 600, 6,000. That's 60,000. I am struggling today. And then like 6,500. What family is it from? It doesn't even say that. I'll tell you what it says in a minute. What family would this element probably be from? Family 1. Why? Because once you remove 1, which is what family 1 has, then you had the large leap. Okay? The question really says, now that I remember it in my head, it gives you this stuff, and then it complicates things. It says the atom would most likely form a bond with oxygen in what ratio? 2 to 1. All of family 1 elements is a 2 to 1 ratio. Did that make sense? You guess? What? Okay. Someone says they don't get it, and I'm reading eyes. There's a lot more than one that doesn't get it. Seth's rubbing his head. He's thinking I should have listened to Abby and Jerome. So for a second, tell me if you're okay that this element is from family 1. Raise your hands if that part made sense. Okay. All right. No. All right. Look at this chart. This chart shows the leap between a relatively small number and a large number for sodium was after 1. For magnesium, it wasn't until after 2. For aluminum, it's not after 3. It's because removing a valence electron is easy. Removing a core electron is extremely hard. So when you look at the data, you find where the large jump is between, and that tells you there was 1 valence electron, which means this must come from family 1. Now, why would it form a 2 to 1 ratio with oxygen? It's because family 1, I'll just pick H, that's from family 1, right? When it's with oxygen, 1, 2, 3, 4, 5, 6, H can only give 1. It has 1 valence electron. So oxygen must need 2 of them to fill its octet. Now it's happy. It's crazy. Loco, chemistry, bonkers. Is that better? Better? Maybe. All right. Okay, that's how the question's asked. It's a take home, and I just gave you the answer on video. No reason why you should get that wrong. It's roughly at the like 20-minute mark even of today. Okay. because it might be hard to find that when you're trying to Google all the answers. That's a complicated one to type in, unless you do a Boolean search. Anyone know what that is?
No.
One nerd, two nerds. Okay. You should learn what those are. Okay. Ionization energy. I'm going to call it good enough. Okay. Next is electronegativity. Of all the things we talk about, we probably talk about this and apply it more than everything else, but it only gets one slide. Because we love it the most, and it's really easy, and quote unquote, Bert already taught me this, and quote unquote, eat it, and quote unquote, yes. Yeah, this is the ugly hotness scale. All right, so electronegativity is, let's see here, is the tendency of an atom of a given element to attract electrons to itself when bonded to another atom. I don't know if that's what it says. That's pretty much what it means to say. All right, so it's the ability to like steal the other atom's girl. Yeah. Okay. If you're taller, better looking, richer, straighter teeth, have confidence, boys, that's all that actually matters in the long run. All right, to actually look them in the eye and talk, all those things, you can steal their girl. All right, helps if you sing. All right, if you play the bass, right there, those boys, you're just stealing girls all the time. Typically, soccer players are pretty attractive people. They're not supposed to be short. Okay, so here we go. Please look at this arrow. Electronegativity is very similar to something else that we've talked about. Zeph, it's the same again. Fluorine is the absolute hottest. That's my wife. Okay. Nope. And I'm not even, my wife is beautiful, but what I'm saying is like, I'm a pretty cool dude in my home. I tell my kids 95% of what to do, but someone can always overrule me if it has to. And that's Fluorine. That's my wife. Right? In your home, and sorry if your home's not like this, I don't mean to make you feel bad, but like dad, he can yell and get mad, but who runs? Melanie. Okay, like I'm there to make money. All right, that's ultimately my only role. So okay, now so fluorine has the ability to tell every other atom how they're going to do whatever they're going to do. It is the hottest, best looking, bad-est person ever. Fluorine, 3.98, usually just rounds to 4. You don't need to know the units of that. You just need to know fluorine's a big number versus the ugliest, biggest loser right here, right? Francium, cesium, radium.
How does France feel about the fact that it's called the elements?
Have you? You took my line. Have you? They're the same continent. Anyway, so electronegativity, the ability to attract an atom is 100% tied to Zeph. The size of the atom is 100% tied to Zeph. So small atoms are very electronegative. Large atoms are extremely non-electronegative.
And also attractive.
They're attractive in a different way. They're attractive in that you're like, oh, I could totally steal that guy's girlfriend. Like they're the easiest prey. There's like, francium's probably like already hanging out with someone over here. And then fluorine's like, no, you're done. All right. and it just kicks them out. It's over. And you know what? The other people have no choice. Like, but I love you. But it don't matter. You ugly. Okay. There's an old Far Side. It's one of my favorite ones. Yeah. The aliens taking someone, and the guy's like, take me, take me. And it's like a bubble. It's like, no, you're ugly. Okay. Lots of jokes aside, whatever. Just remember, fluorine, very electronegative. Fluorine can attract any electron to itself in a bond. These cannot. Now, this is coming up soon, but a bond between these and these is a strong bond and has a name. Ionic. These two, you got a loser and you got a taker. When they lose, they form cations. When they gain, they form anions. And when they hang out together, it's a bond between ions. So we call it an ionic bond. Because really, fluorine's super good looking, but like if it lives in a cabin in the hills all by itself, who cares? He ain't stealing no one's friend, right? Fluorine has to be around someone until they're interpreted to be attractive. And then, boom, electrons all over that.
So basically, he could be the ugliest person on there. This is the most
Yep. It's the most what? Oh yeah, chemistry is super deep when I teach it the wrong way. All right, sort of okay with electronegativity. It's just the ability to attract electrons to itself in a bond. Okay, we've known this forever. You learned it in biology. What did we learn? You learned two total things in biology. Mitochondria. Water's polar. Does that sound familiar? Whoa, I lost my balance. Water's polar. We'll learn what that means, but it has everything to do with electronegativity. No. Did you say the word lipids? I'm out. I got lipids, but I don't know anything about them. Okay, look up here. I'm not going to write hydrogen. Water's H2O, correct? Okay. Oxygen from this chart has an electronegativity of 3.44. I don't know exactly, but it's 2.1 something for hydrogen. Stick with me.
Wait, so what if you like put fluorine in water?
The world ends. Well, you make hydrofluoric acid. Okay, here we go. We'll talk about that too. But here you go. This is its ability to attract an electron when bonded to another atom. That's oxygen's. So if the electrons are right here, they're not really right there. Where are they? They're closer to, I can just look that way. Duh. Okay, can I? All right, they are closer to the oxygen. Why? Because oxygen's more attractive. Now, it's not a large enough difference in attractivity. Is that a word? I don't care. To like completely remove, that would be an ionic bond, but it still attracts the electrons here. All right, and then there's another pair. It attracts its electrons right here. You with me? Okay, now this is complicated, but oxygen has 8 protons and usually 8 electrons. But for right now, these are hydrogens, not 4. I don't know if I got confusing. But now there's sort of 2 more, which makes how many negatives? -10, right? Now, it doesn't really remove them, but can you just go with me? that now this part, the oxygen's a little more negative than it was before. Can we all agree to that? Because it's good looking and the electrons move towards it, which means this must be what? A little more positive. Okay, question?
Oh, so that's why it's saying one side is negative and one side is positive. So
Yep.
it's supposed to be-
That's where we're going. We say water's polar because it is more electronegative. It pulls the shared pair towards it, which makes this side have the little sigma minus. Remember that from whatever? So it's like something ugly like that. I could never do. All right, that's better. It's a sigma for now. No. Like that, but that's not how we do it. Okay, doesn't matter. Let's not fight about stupid things like that. It makes, we don't put an official minus because it's not negative. It's partially negative and partially positive. Okay, now Aisley sort of already like gave it away, but not that it was rocket science. I don't remember how the triangle tool works. That's about not how I wanted it.
Almost from you draw a rectangle that the triangle is within.
Okay, well, anyway, don't care. If I divide this triangle in half, this part is what? And this part is positive, which makes it two-sided. And the word we use for sided in high school chemistry is called polar. And physics, by the way, because we have the planet and we have the North Pole and the South Pole. Polar means two-sided. Okay with that? Like we won't go into any details, but the last election was extremely polar. You either hated one and loved the other, or loved the one and hated the other, right? There was no middle ground. Like, I think they're okay. No, not a human on the planet exists. It was one or the other. It was a very polar election, two-sided. This water molecule, polar, due to electronegativity differences. Fair enough? Okay, I'm moving on. Electron affinity is the least important of all of them. Like, it's usually not tested when I say least important. Might be the most confusing as well, but what else? No, you do. All right, so pause for a second. Just look at this picture. Ionization energy is the energy required to remove an electron. You okay with that? To make it an ion. Electron affinity is the reverse. The energy you get back when an electron is added to an atom. So it's the opposite. They are opposites of each other. Now, they're not perfectly opposite. You'd think, oh, well, if ionization energy is 495, electron affinity must be negative 495. Way false. Don't think that they're really that way. Okay, now, affinity. It's the energy change accompanying addition of electrons to a gaseous atom. Okay. Now, it's pretty, chlorine plus electron goes to Cl minus. Well, that's kind of normal. We're used to that, right? That's what it wants to do. But metals can gain electrons as well. Do they like to? No, but they can. So here we go. Now, before we get here, I have this random slide. When we have an ionic substance, this is coming up pretty soon. When you have an ionic substance and we want to know the energy involved in the reaction, we look at the metal that loses and we have its ionization energy. That's the energy that is required to remove an electron. And then we look at the nonmetal and we look at the energy given off when the electron is added. And that's the electron affinity. So it is sort of important because this is the comparison that we're going to make. That looks almost like something to do with music, but I'm losing my mind. Okay. That's a 50-second note. Oh, I was sort of close. Okay, moving on. So like, it's not something we use a ton, but it is something applicable to what we're doing. That's all that was for, besides the random whatever. I was a star in choir. Yes, thank you. I'm the most monotone baritone you ever met. Okay. In general. Now, this is a super generalization. That got him. That's him? You're the monotone baritone?
I am not the monotone baritone. I'm not even a baritone.
There's like 3 notes. I'm all over. I can hit those every time. Like at church, like money note, money note. Oh, how do I go there? What gets me at church? And this just sucks. Whoever writes music sucks. Is there 5 lines? Okay. Huh? Yeah, I remember. You get 10 notes in a row that are like right here. And then for some reason they think it's important that you go here. And then they expect you to know how to go there. I do not understand it. Now you singers are like, duh. But us normal humans, look, I can go here. I can do that. I do that a lot, especially if the tenor note's like right there. I'm a tenor for like a beat or whatever it's called. Like, I'm just gonna rock that. But why? That's just terrible for us. Is anyone on my team in this argument? Okay, thank you. Okay, moving on. Sorry, I distracted. Here we go. This is the least dependable chart of all of them. Like, these numbers are true, but when I say in general, I mean like super generally speaking, because there's all sorts of variability in here. So don't look at me like, well, why is that one, that one, that one, that one, that one, that one? I don't know. Here we go. In general, and it's weird because it's negative numbers. Electron affinity becomes more exothermic as you go from left to right. Look, everyone on the planet wants to say electron affinity increases as you go right to left, which is true, but it's a negative number because it's, I said it right, correct?
Well, you were saying left to right, which is correct, but
Okay,
I'm
okay,
requesting something.
okay. So electron affinity is high for fluorine and low over here. But it's an exothermic value. So that's why it says it becomes more negative or more exothermic as you go to the top right. But it is increasing, even though negative 328 is technically a smaller number than negative 122. Electron affinity, high for nonmetals, low for metals. Are we all right with that? Okay. What's that? They're built different right here again. And why? It's the same thing. Right. We got 1, 2, and then we're here, or are we here? So it's all about filling or emptying something that's half full or full. So, but don't stress about the discontinuities. Are we sort of okay? Electron affinities, very exothermic, and then not. And then look right here. Helium and all the noble gases, it's not an exothermic number. So they require energy to add an electron, and they require a ton of energy to remove an electron. So will they ever naturally form a bond? Never, ever, ever, ever. Yep.
What happens when you do form bonds? Like, what-
It just takes energy. Takes energy. And these, since their electron or their ionization energies are relatively low compared to the other ones, these bonds can happen. And they're weird. They're usually like Xe6F4 or something random like that. I can't remember exactly what they are, but they're like weird and massive and kind of cool. We'll draw them out actually in the next couple weeks. But typically speaking, that is that. Okay. I think that's just the white space of happiness. Right? Okay, there's some room. Is there room somewhere? Okay, here you go. Draw yourselves a periodic table.
Oh my gosh.
All right. This is what I would like you to do. Ugly. Draw a rough sketch of the periodic table below or to the right. Use arrows to clearly label the following trends: electron affinity, ionization energy, atomic size, reactivity. I haven't really talked about reactivity, have I?
Nope.
All right. Reactivity, pretty simple. Reactivity over here, if something has a high Zeph, it has a great ability to get an electron, correct? Or it's very reactive. Down here, these large atoms cannot hold on to their electrons very well. That means they're going to be really reactive. So the biggest losers and the best stealers are your most reactive elements. So that one's going to have two sets of lines, and it's the only one. I'll just show you right here. So reactivity, I'm going to say is green. And then I would say reactivity okay, see if you can label that up. Let me pause this. I'm not going to label them all because this might be on your exam, which I should start printing. All right, do you feel, well, we'll find out when you read your exam tonight, right? Or on Christmas break, losers. I should, but it's a test question, so.
So you're supposed to get us ready for that test.
I have on the previous 20 slides. How's your leg?
We have the slides right here.
Your knee all right?
Yeah.
How's your pride? Your pride.
Right. I was like, I think right.
Oh, you did not.
No, it's actually maybe my side backwards.
Oh. All right, I'm going to end this. Good luck. Yes.
Wait, you have a test for us?
Yeah.